Okay, so let us look at how to load the text data and create input pipelines based on the text data. So, in this case we use tf.data.textLine dataset to load examples from text file into a dataset. The TextLine dataset is designed to create a dataset from a text file in which each example is a line of text from the original file. This is very important to note that each example is a line of text from the input file. This is potentially useful for any text data that is primarily line based. This kind of data sets could be a poetry or error logs or movie reviews, for example. So, let us start by importing Tensorflow and Tensorflow dataset. We will be using 3 different English translations of the same work, that is Horner's Iliad, and see how to use TextLine dataset and other preprocessing on the text to create a dataset that can be fed into the model for training. So, we have text of 3 translations as input. So, there are 3 files cowper.txt, derby.txt and butler.txt, which is translation of Homer Iliad. We first download these files and then print the parent directory. After getting the data, the normal preprocessing tasks are about removing document header and footer, line numbers, chapter titles if those are present in the file. So, you can see that now the files are downloaded and they are in root/.keras/datasets directory. Now that we have downloaded the files, we will go through each of the file, we will load them into a dataset. Each file will be a single dataset. We need to label each example. For that purpose, we use dataset.map function that applies a labeler function on each example. So, labeler function takes an example and assign a label to that particular example, and we do that with a map function. So, map will iterate over every examples in the dataset and will return example comma label pairs. So, let us apply the labels on each of the example by running this particular code cell. We will combine this label dataset into a single dataset and shuffle it. For that, we set the buffer size to 50,000. We are going to use batch size of 64 and we will look at 5,000 examples. So, let us concatenate the individual datasets into a single dataset. So, you can see that first we copy the first dataset into all label data, and then for the remaining datasets we iterate over remaining datasets and concatenate them to the all label data. So, at the end of this particular process, all the datasets are concatenated into a single dataset, which is all label data. After concatenating all datasets, next we shuffle the datasets using the buffer size of 50,000 and we set the reshuffle underscore each underscore iteration parameters to false. So, we do not want to reshuffle the dataset at each iteration. Then we can use take and print functions to see what example pair look like. So, what we do is we take 5 examples from all labeled data and we print each of the example. Let us see what it brings up. So, you can see that we have 5 tensors for first 5 example, 1 per each example. You can see that each tensor is a scalar quantity or a 0 dimensional tensor. It's of type string, and you can see that we see the string corresponding to this particular tensor, and corresponding to each of the sentence there is a label associated with it, which is another scalar, and the label for the first sentence is 0. Second sentence is over here and it has got label of 1 and so on. So, you can see the first 5 examples or first 5 examples from all underscore labeled underscore data. Now, you know that machine learning models work on numbers and not words. So, naturally what we need to do is we need to convert these words into numbers. So, one way in which we can do that is we can map each unique word to a unique integer. So, first we build a vocabulary by tokenizing the text into collection of individual words. There are few ways to do this both in Tensorflow and Python. Here we will iterate over each example and we will tokenize each example into tokens. We then collect each of the tokens and remove the duplicate. So, you can note that the vocabulary set is a set that we update with the tokens that we get after tokenization. So, the effect of that is the duplicate tokens are removed. And finally, after completing the process for each sentence, we can find out how many words are there in the vocabulary just by taking the length of the vocabulary set. Let us run this code cell and see how many words are there in our vocabulary. So, we have 17,178 words in our vocabulary. We create an encoder by passing the vocabulary set to token text encoder, which takes a string of text. The token text encoder has encode method that takes a string of text and returns a list of integers. Let us try it on a single line to see what output looks like. So, what we do is we take the example text and we encode that example text with the encoder defined over here, and then we print the encoded example. So, you can see that the first text here is we may attempt to give his reg a check. Let us see how this example is encoded. You can see that each of the word over here is encoded with a unique integer. Now that we have seen how the encoder works on a single example, we will apply the encoder on each example in the data set. For that, we wrap the encode under tf.py function. The encode function takes a text tensor and label and returns the encoded text along with its label. So, we use tf.py function to wrap encode and we give the text and labels as inputs. So, we use a map function to apply the encode underscore function underscore map on each example, so that each line gets converted into its numeric representation. The next task is to split the data set into test and training batches. We use tf.data.dataset.tex and tf.data.dataset.skip to create a small test set and a large training set. Before being passed into the model, we need to batch the data set. Typically, the examples inside a batch need to be of the same size and shape, but the examples in these data sets are not all of the same size. Remember, each line of text had a different number of words. So, we use padded underscore batch instead of a batch to pad each example to make it of the same size. So, let us see how to do that. So, let us first see how to construct the training data. So, we take all encoded data and we skip first 5000 examples, because we have taken take underscore size to be 5000, and then we shuffle these examples. So, by skipping the first 5000 examples and shuffling, we get the training data, and we take these 5000 examples that we skipped in the training data to form the test data. Then for training and test data, we apply a padded batch, so that each example is made of the same size by padding. So, let us run this code cell. Now, we have test data and training data ready. So, test underscore data and train underscore data are not collections of examples comma labels, but they are collection of batches, and each batch is a pair of many examples comma many labels represented as arrays. Let us look at the first batch. We use an iterate over the test data and we take the next. So, this next returns the text and labels, which we store in sample underscore text and sample underscore labels, and then we examine them. So, you can see that the first example is already converted into numbers and it is padded with 0, so that its length is equal to the length of the longest sequence in the data set, and we also have a label which is 0 in this particular case. Okay. Since we have introduced a new token, that is 0 for padding, we increase the size of vocabulary by 1. So, these are steps that we take in order to convert the text data into data sets. or in other words we use text line dataset method to construct dataset object from the text data. Now that we have constructed training and test data, we can use that for training the model. Let us understand how we can process Unicode strings with TensorFlow and also understand how to construct dataset objects with Unicode strings. So, we can use TensorFlow to process different languages with different character sets. Unicode is a standard encoding system that is used to represent characters from almost all languages. Each character is encoded using a unique integer code point between 0 and this particular number. A Unicode string is a sequence of 0 or more code points. So, the tf.string d type allows us to build tensor of byte strings. Unicode strings are UTF-8 encoded by default. So, let us see how this thanks with emoji is represented. We can define that with tf.constant. A tf.string tensor can hold byte strings of varying length because the byte strings are treated as atomic units. The string length is not included in the tensor dimension. Let us look at the shape of these two strings, which has UR and welcome as two strings. So, you can see that this is a tensor which is a vector containing two elements, or in other words, this is a 1D tensor with shape 2. There are two ways to represent a Unicode string in TensorFlow. One is using a string scalar or integer 32 vector. The string scalar stores the sequence of code points with a known character encoding, whereas integer 32 vector stores each position containing a single code point. So, as an example, the following three values are represented in a Unicode string. This is a Chinese character for language processing. Here we are using Unicode strings represented as a UTF-8 encoded string scalar. So, you can see that this is a scalar with D typed string and we have UTF-8 encoded string scalars. Here we have a Unicode string represented as UTF-8 16 BE encoded string scalars. And finally, we have the same Unicode string represented as a vector of Unicode code points. So, you can see that this text character is a vector containing 4 elements and each element is a Unicode code point corresponding to the character. So, this 35821 is the code point corresponding to this particular character, 35328 is the code point corresponding to this character, and so on. So, there are 4 characters and there are 4 code points corresponding to each one of them. So, we just saw 3 ways of representing strings, one using UTF-8 encoded string scalar, then UTF-8 16, then UTF-16 B encoded string scalars, and as a vector of Unicode code points. TensorFlow provides operations to convert between these different representations. We use tf.strings.unicode decode to convert an encoded string scalar to a vector of code point. Unicode underscore encode converts a vector of code points to an encoded string scalar, and Unicode underscore transcode converts an encoded string scalar to a different encoding. Let us look at the examples. Here we use Unicode underscore decode. So, here what will happen is this text underscore UTF-8 will get converted to a vector of code points. You can see that over here. So, this was a scalar, it got converted into a vector of code points. Let us take the vector of code points and convert that to a string scalar using Unicode underscore encode method. When we apply that, the vector of code points get converted into a scalar, a string scalar encoded in UTF-8. Finally, we can use encode underscore transcode to convert between UTF-8 encoding and UTF-16 B encoding. So, the input encoding is UTF-8 and the output encoding is UTF-8-16-BE. When decoding multiple strings, the number of characters in each string may not be equal. So, it returns tf.track tensor, where the length of innermost dimension varies depending on the number of characters in each string. So, let us take an example. We take a batch of Unicode strings, each represented as a UTF-8 encoded string. So, we have hello, what is the weather tomorrow, then good night, and an emoji for smiley. We use encode string function that returns, we use Unicode underscore decode function to convert the characters into a string of Unicode code points. So, we get a rack tensor, and you can see that the length of each vector, resulting vector, is different. We can use this rack tensor directly or convert that into tf.tensor with padding, or to tf.sparse tensor using to_sparse method. Now, here we converted the rack tensor to a dense tf.tensor. Here we pad each example with -1, so that lengths of all the examples, are the same. When encoding multiple strings with the same length, a tf tensor may be used as an input. When encoding multiple strings with varying length, a tf.track tensor should be used as an input. If we have tensors with multiple strings in padded or sparse format, then convert it to a rack tensor before calling Unicode encode. Let us look at some of the Unicode operations. Let us see how to find the length of the Unicode string. So, the tf dot strings dot length has a parameter unit which indicates how length should be computed. Unit defaults to bytes, but it can be set to other values such as UTF-8 underscore characters or UTF-16 underscore characters to determine the number of Unicode code points in each encoded string. So, let us take an example where we take thanks and smiley emoji and encode that using UTF-8 encoding, store that in the thanks, and we can use the length without any argument. So, we get number of bytes, and if you want to find out number of characters, we specify the unit as UTF-8 underscore characters and get the length. So, let us check the result. So, this particular string is encoded with 11 bytes and there are 8 UTF-8 characters. We can use tf.strings.substr operation to get character substrings. It also accepts unit as it also accepts the unit parameter and uses it to determine what kind of offsets the position and length parameter contain. Here the default unit is byte. With length 1 we return a single byte. Here the unit is UTF-8 character and we return a single character, which in this case is 4 bytes. So, are you getting the difference between substrings here and substring here? Here we are not specifying unit. So, by default byte is taken as the unit. So, here we get a single byte and here we get a character, single character, which is 4 bytes. We can also split the Unicode string using Unicode underscore split operation. To align the character tensors generated by tf.strings dot Unicode underscore decode with offset, to align character tensors generated by tf.strings Unicode underscore decode with the original strings, it is useful to know the offsets for where each character begins. The method tf.strings.unicode underscore decode underscore with underscore offsets is similar to Unicode underscore decode, except that it returns a second tensor containing the start offset of each character. So, let us use Unicode underscore decode underscore with underscore offset on a string of emoji which is encoded in UTF-8. It returns code points and the offsets. We print the offset and the code point. you can see that the first emoji is represented with code point 127,880. The second emoji is encoded with this particular code point, and third one is encoded with this particular code point. And we also get corresponding byte offsets of each of the emoji in the original string. Each Unicode code point belongs to a single collection of code points known as a script. A character script is helpful in determining which language the character might be in. For example, knowing that this particular character is a Cyrillic script indicates that modern text containing that character is likely from a Slavic language such as Russian or Ukrainian. Tensorflow provides Unicode _script operation to determine which script a given code point uses. The script codes are, so you can see that they have script 17 and 8. 17 corresponds to Han Chinese and 8 corresponds to Cyrillic.